Okay.
Hi everyone. So I'm Deep. This is Kevin. That's Hattie. That's David. And we'll be talking about the HighHeatFlux thermal management. So before we talking about thermal management, the motivations for our project is that in applications such as electronics and electric vehicles, there's a need for high power dissipation, and so one of the reasons the FRL wanted us to research on power dissipation was so materials wouldn't degrade and fail under high power consumption. This is some of the work that's been done previously. Basically, the copper rod, which was fabricated to dissipate the heat, in which a cartridge heater at the top is supplying the heat, and at the bottom, the cooling technique is employed. And so on the left, side, those are the two different techniques that were used before. There's like a cold plate at the bottom, which dissipates the heat, and the other one is just simply just putting in water and allowing boiling to take out heat. The heat flux that was issued was 60 to 120. Our aim is to get 500 watts per centimeter squared, and so these are our objectives: create the system, mounting system, actually cooling it, and then creating a vapor chamber. This is the requirements provided from the AFRL. And essentially, we want to achieve a minimum of 500 watts per centimeter squared. This is the like milestone. Not really timeline, but for fall, our goal is to test with water. For winter, it's finally use liquid nitrogen and then present the data to the AFRL. And then spring, just optimize our spray angles and jet profile. Our two advisors are Professor Rafiki and Professor LaRue. This is our organization. We have like 4 sub-teams, and all the sub-team leads.
Okay, so I'm the installation sub-team lead, and our objective is to create the actual chamber that's going to house the copper rod while it's being heated. And the material we're going to use, our objective is to have it have a high max temperature. So we're going to use ultra high temp rigid calcium silicate sheets. And the good things are machinable, so we can shape the entire box into the shape right here. And we purchased extreme temperature cement to coat this holder because it's going to be in direct contact with the rod. The holder cannot withstand temperatures above about around 650 degrees Celsius, and the rod is going to be higher than that. So the extreme temperature cement is there to protect this holder here. And the dimensions of our box are going to be 5.5 inches long, 4 inches wide, and 6 inches in depth. And the cost of the calcium silicate sheets is $15.83 per sheet. We've so far purchased 3 sheets and 1 8-ounce tub of cement to coat this. So here's the progress for our sub-team. We have our SolidWorks model created. We identified machinable insulation. It has a max temperature of 1700 degrees Fahrenheit, which is around 650 degrees Celsius. It's non-hazardous, and it can be worked with regular woodworking tools, so that's good for us. And the extreme temperature cement, again, is to protect the holder from temperatures of greater than 1700 degrees Fahrenheit. The extreme temperature cement goes up to, I believe, 2700 degrees Fahrenheit, which is more than 1000 degrees Celsius. So that's more than enough than we need. And so far, the boards and cement have been purchased, and this week we hope to have the boards cut to their proper dimensions. And we're ready to coat the holder in the extreme temperature cement to have it ready by week 10 for our water test.
So I'll be talking about the liquid nitrogen spray system. So our main objective is to basically develop a system where we can cool down our copper rod. This is different from previous iterations because previous iterations we used water, but this time we're using liquid nitrogen due to the fact that it has a lower temperature. That it is around negative 196 Celsius compared to the 0 degrees for water. And we also chose liquid nitrogen due to the fact that it's affordable and really available at the UCI science store. In order to integrate our liquid nitrogen into our system, we plan on connecting a LN2 hose to the vapor chamber. We decided to enclose the vapor chamber because we don't want any of the liquid nitrogen pouring out. That could be potentially dangerous. We plan on adjusting the angle of the LN2 spray hose. That way we can pick out which angle it can be more efficient for contact. For our task, we talked with Dr. LaRue about specific designs. Originally we thought of a cryogenic pump, but we realized that it was unattainable due to time constraints and also money constraints. In addition, we also talked to cryogenic accessories. We thought it would be better to rent their equipment. Also negotiated the price, and we plan on placing an order for our LN2 tank soon. In addition, we're also analyzing safety concerns about handling LN2. We're looking at how different can be approach handling of LN2. For future tasks, we plan on testing with water. That way we can have a reasonable data sample size so that we can compare it to our LN2 test. And yeah, that'll be it.
So while conducting this experiment, we're going to be creating a vapor chamber. The main objective of the vapor chamber is to actually house the experiment. So LN2 is actually a very dangerous coolant. So what our main concern is safety. We want to make sure that burns, hazards don't occur. So possible hazards from LN2 is burns or asphyxiation. Asphyxiation is causes the environment to become low oxygen atmosphere. So we are planning to conduct the experiment inside a vacuum sealed box with a baffle system for ventilation. The materials we plan to use for the frame is a A20 quick frame. The parts are listed onto the right here. Our main purpose for selecting these materials is because we want something that's easily accessible, because we will be opening this ventilation or this vapor chamber quite frequently to change the angle of attack or for any possible adjustments that we might need to do. The dimensions of our box right now is 17 inches in length. Width is going to be 12 inches and a height of 12 inches as well. The following right here is the cost of materials that are going to be used to create this vapor chamber. The ones that have NA on it are either materials such as the plexiglass we have already gotten from AFRL, but materials such as the nozzle stand and the vacuum haven't yet been determined as to which one we're going to use. So some of the completed tasks that we have achieved are we have personnel that are already trained in cutting the plexiglass or machining some of the metals that we're going to be receiving from the 8020. We have identified the hazards that we are going to be encountering when conducting these experiments. That's a very important part of this project. Determining the frame design and fastening methods. Reviewed some of the designs with Dr. LaRue. So when we reviewed our initial design with Dr. LaRue, he wanted us to incorporate the baffle system for ventilation. Since we are not going to be able to get all the vapor out of the chamber all at once, he wants some sort of outlet for the vapor to go through. And we have identified some of the necessary requirements for our vapor chamber. Some of the tasks that we have in progress is building a prototype. So we have Professor Fink wants us to conduct the experiment using water. So we will build a prototype that doesn't have to necessarily be as secure as our final design. We will be using some of the materials that we have obtained from the AFRL. And we are resizing the plexiglass right now for the chamber, for the walls of the vapor chamber. And we are still researching the possible nozzle stands that we want to use. Since the hose of the LN2 will be getting cold, we want something very insulated and something that is also adjustable. Future tasks that we have to still yet to complete is to test and evaluate the prototype. Order materials, and after testing and evaluating the prototype, we also need to see what worked and what didn't work, and if, see how we can redesign and improve upon our design that we have already. And finally, build and test the final vapor chain.
Okay, so this is our third budget. We have enough already with our team members, like 1,300. So and again next quarter, so we don't really need like figure out. But this is like a base budget. As you can see, the door is like 450. That's like we're going to be renting it. So